Hello, sir. Uh, I am going to discuss four problems of transport phenomena in this video. So, my first problem is three miscible fluid flows between two parallel plates at the gap of 6 into 10 to the power minus 3 meter. So, in this problem, I need to derive momentum flux profile and velocity profile across given gap by using Newton's law of viscosity and shell momentum balance approach. So to derive this expression, we need to take some assumptions. First assumption is that flow is a steady state and fully developed laminar flow, and fluids are incompressible Newtonian fluid. And so we need to take Cartesian coordinate according to our system, and origin at bottom plate left near corner. So we can clearly see that velocity is only in z direction. Velocity is only in z direction. So and velocity vz is function of x. So shell element start with x end and end at x plus delta x with length L and width W. So we can apply here shell balance equation. Since viscosity of each fluid is approximately same 0.1 Pascal second, so we can consider a single fluid in given entire gap. So our shell balance equation will be rate of momentum flux, momentum in by convective transport, and rate of momentum out by convective transport, plus rate of momentum in by molecular transport minus rate of momentum out by molecular transport plus force of gravity acting on system is equal to 0. So by applying this equation and given boundary condition at x is equal to 0, vz equal to 0, at boundary condition x is equal to 3b, vz equal to 0. So by substituting all the assumption in given cell balance equation, we get shear stress tau xz delta p by l x plus constant c1, and velocity profile vz is equal to minus delta p by 2 mu l x square minus c1 mu plus constant c2. So by applying boundary condition, we can find constant c1 and c2, where c2 is equal to 0 and c1 is equal to delta p 3b by 2l. So after substituting all constant, our final expression for flux profile and velocity profile will be tau xz is equal to delta pb l by into x by b minus 3 by 2, and velocity profile will be vz is equal to 3 delta p b square by 2 mu l into x by b minus x square by 3b square. So our according to our expression, our velocity profile looks like symmetric parabola, and flux profile will be linear and 0 at center and maximum magnitude at walls. So according to our question, we have derived flux profile and velocity profile. So now our second problem is based on above derived expression. So in this problem, we need to calculate velocity and flux at given distance. So uh, here properties are given. Fluid 1 density of fluid 1 934.58, and kinematic viscosity is given in of three fluids. So we can calculate dynamic viscosity by using mu is equal to rho into mu actually. So we can clearly see that here viscosity is approximately same for each fluid. So we So system acts like single fluid. So here now we can calculate pressure gradient delta P by L is equal to 15,000 by 0.7, which is approximately 21,428.57 Newton per meter cube. Here, due to symmetry, tau is equal to 0 at center, which distance is equal to y is equal to 3 mm. So here compact form of flux profile and velocity profile is already given in our question. So actually not question, we have previously derived. So according to this expression, we can calculate velocity and flux. So here you can see the table by substituting each variables, and you can get this value of velocity and flux. So now our third problem. In this problem, a viscous liquid is being pumped upward through a vertical cylindrical pipe. The flow is driven by pressure gradient and must overcome gravity. Okay. So our data is given: pipe radius of pipe and pipe length 5 meter and radius 25 mm, and density of fluid is 950 kg per meter cube. So here's one cylindrical pipe is given and fluid is flow upward by overcoming the gravity, and we need to calculate the combined pressure at the inlet and outlet. So and here also second part of the question is using the shell momentum balance. We have already result. So Vz is equal to P naught minus PL by 4 mu L R square into 1 minus R by R square. So we need to calculate the velocity at center line. R is equal to 0. So for part 1, combined pressure at inlet, we apply the formula P is equal to P naught plus rho g. So at inlet R is equal to 0. When we substitute the pressure here, so second term will be 0, and combined pressure at inlet will become 2.5 into 10 to the power 5 Pascal, and at outlet we again apply the same formula. Combined pressure PL is equal to pressure at inlet and plus rho GL term here. So we can calculate combined pressure at outlet 1.466 into 10 to the power 5 Pascal. Now at center line velocity, at center line R is equal to 0. We have expression for the calculating the velocity. So by substituting all parameters, we get velocity at center 26.93 meter per second. So now move to fourth problem. So in fourth problem, fluid is flowing the gap between two concentric cylinder. In this problem, concentric cylinder are given. Outer cylinder is at stationary position and inner cylinder is moving. So we need to calculate the velocity, radial velocity at distance of 4 mm, and also we need to calculate the momentum flux due to motion of fluid at the surface of inner cylinder and at the surface of outer cylinder, which is stationary, at R is equal to 6 mm. So for this given system, we have velocity profile Vz is equal to V into ln R by R out. Here R out is outer radius of stationary wall, and inner radius is equal to 2 mm of inner cylinder, and viscosity of fluid is 0.45 pascal second. So here we need to assume pressure gradient is zero. Flow, that means flow is here we consider only that flow is only by moving inner cylinder. Flow of fluid is only moving by inner cylinder. So according to given expression of velocity profile, we can calculate velocity at r is equal to 4 mm. So by substituting all parameters, so we get velocity 0.738 meter per second at r is equal to 4 mm. So now we need to calculate momentum flux. So using Newton's law of viscosity, tau rz minus is equal to minus mu dvz by dr. So by substituting above expression vz and differentiating the expression, we get momentum flux. Momentum flux tau rz is equal to minus mu v by r ln r in by r out. So by substituting value of r, we get momentum flux at r is equal to 2 mm and r is equal to 6 mm. At r is equal to 2 mm, momentum flux will become 409.6 Newton per meter square, and at r is equal to 6 mm, 136.5 Newton per meter square. We can also calculate total drag force. So drag force is equal to nothing but shear stress and the surface area of the inner cylinder. So surface area of the inner cylinder will become 2 pi r of and inner radius of cylinder and length into length. So by substituting all values, we get total drag force is equal to 2.57 Newton. So thank you, sir.